Welcome. In this video, I will be going over a classic application of the dot product. So what we want to do is we want to express this vector v, which is negative 4i plus 2j, as the sum of two vectors such that one of these vectors is parallel to this vector u, while the other is orthogonal to u. Then we're going to verify our result using technology. First things first, let's call the parallel vector P for parallel, and the orthogonal vector N for normal. Now, using these names for these vectors, P and N, our goal becomes writing V as P plus N. Let's start by finding P, since recall that the projection of this vector V onto U is parallel to U, so that'll be our parallel vector. And that's equal, and this is equal to the dot product V and U divided by the magnitude squared of U, which we can just write as U dot U, and then dotted with, again, vector U. This equals negative 4 times negative 2, so we're dotting V and U, plus 2 times 6, divided by U dotted with itself, so negative 2 squared plus 6 squared. And then, of course, we have vector u here again, negative 2 comma 6. Well, this is 8 plus 12 divided by 4 plus 36 multiplied to negative 2, 6. So we have 20 over 2, oh, not 20 over 2, excuse me, 20 over 40. I'm getting ahead of myself here. Multiplied to negative 2 comma 6, and then bear with me, I'm going to rearrange real quick because I took up too much horizontal space here. So I'm just going to shift this. There we are. And I'm going to also zoom out just a little bit. There we are. So this is 1/2 negative 2, 6, which is just negative 1 comma 3. So our vector P is equal to negative 1, 3. Now remember, our goal says V vector is the sum of the P vector plus N. That tells me that N is just equal to the vector V minus the vector P. So V again is negative 4 comma 2, and from that we're going to subtract P, which is negative 1 comma 3. So this becomes negative 4 plus 1, which is negative 3. And then we have 2 minus 3, which is negative 1. All right, so what have we found? We have found that P is equal to negative 1 comma 3. V, excuse me, not V, N All right, let's summarize our results. P is equal to negative 1 comma 3. N is equal to negative 3 comma 1. And now let's verify this using technology. As you can see, I have GeoGebra up, and I'm going to go ahead and open my favorite, which is GeoGebra Classic. And then I'm going to go ahead and plot my origin there, O. And I'm going to let V equal our definition of vector V, oops, I couldn't spell for a second, and it is O, comma, open parentheses, negative 2, comma, 6. There's V. Okay, now I'm going to let, P equal vector O, comma, negative 1, comma 3. I think it is very clear, since these two overlap, that V and P are pointing in the same direction. Next, I'm going to let N equal vector, and it starts at the origin O and goes to -3, -1, which I miswrote here on our notes. So let me fix that really quick. There we are. There's that negative I was missing. Okay. And now let's verify the angle between V and N. Angle, and I'm going to type in V comma N. Look at that. It's certainly a right angle. And since all these labels are showing up, I'm actually going to hide that point, the origin. I'm going to say right now hide P. We've already verified it's parallel. And then I'm going to go ahead and move this. And why is this still here? I don't want to see this there. Okay, and here is vector V and vector N. And just to make it easier to see, I'm going to make the font much larger, say 28 points. There we are. That should be a lot easier for everyone to see. Perfect. Now, the last thing I'm going to do is type in P plus N. And look at that. That is certainly what we defined our vector U to be, which was -4, comma 2. Hopefully you found this example helpful. Remember to keep calm and math on.